All right. 5.5 is where we're finally going to actually solve these exponential and logarithmic equations. And we're going to learn a couple different ways to do this. I was going through the homework, and I noticed there was three. There's three that deal with doing some substitutionary stuff that I don't teach in here because it's a little bit tedious, and you're never going to encounter them in any other class from here on out. So I have removed those from the homework. If you previously completed the homework, you just have credit for those if you had missed them. Or if you didn't miss them, kudos to you. We're going to look at how to solve exponential equations, and then we're going to look at how to solve logarithmic equations. And what's interesting is with the exponential equations, there's actually two different ways to do it. The easiest way is this first way, if they play nice. And this states that if you have b to the m equals b to the n, then you can completely ignore the bases and just set the exponents equal to each other and solve. That's the easiest style of problem we can have. So if you are able to rewrite your equation so that your bases are the same with your exponents on top, then just delete the bases and solve for that variable. The first handful of yours will look like this, but the nice thing is even if you don't realize that this can happen, the second way that we solve exponential functions works for everything, and so you don't have to worry about, oh, I didn't catch that that had the same base. If you can't make it into the same base, we're going to use logarithms to solve it, and we're going to see how that works. So here's the first kind of problem. We have 2 raised to the 3x minus 7 equals 32. Now, maybe you realize that 2 to some power is 32, and maybe you don't. So if you were not to realize that 32 is 2 to the 5th power, then what we would do is we would ln both sides. We would take the log of both sides. And I'm going to work it that way first, even though that's not how I work it first in my handwritten notes, so that you can see how we do this. And then we'll show you how to do it if you do recognize that the bases are the same. So if you don't recognize that 32 can be written as 2 to the 5th power, and you need to solve this, what we're going to do is we're going to ln both sides. Remember, as long as we do it to one side of our equation, we can do it to the other. We just got to play balanced. Now, we still have an issue here that our 3x minus 7 is in the exponent. But we learned a bunch of properties last time that allow us to play around with our logarithms. And there's one that's the power rule, where we can pull the power out front. So we can pull the 3x minus 7 out front. ln 2 equals ln of 32. Remember, we're trying to solve this, so we want to get x by itself. So I'm going to divide both sides by ln of 32. And I may want to see if that's going to simplify it all before I start adding 7 to it and all that other stuff. ln of 32 divided by ln of 2. Look at that. It's a nice number. It gives us 5. So to solve, we would add the 7 over, divide by 3, and we find that x is 4. So even if you don't recognize that you could turn 32 into 2 raised to some power, you can still solve it. You just have to do this double ln thing right here. Then you divide. I always recommend checking to see if this simplifies down to a nice number, because if it actually could be the same base, it's going to be a nice number. So you can still do it. If you do recognize that 32 is 2 to the 5th power, which I don't expect you to have these memorized, what I would do is if I have a 2 to some power and then there's an even number on the other side, I'd play around in my calculator and list out some power 2. 2 to the 3rd power, to the 4th, to the 5th, and see if I can't get it set up that way. But 32 is 2 to the 5th. Equals. So when the bases are the same, our rule states that we can just look at the exponents, which is 3x minus 7 equals 5. Notice that's exactly what we got down here after we simplified the ln of 32 divided by ln of 2. So we do the same thing. We add the 7 and we divide by the 3, and we still get the exact same answer. This way's a little bit nicer, but you do have to still do the work on the front end of trying to figure out 2 to what power will give you 32. The way we did it here with the ln's is how you will do it if you cannot get the bases to be the same. Because sometimes you just flat out can't. There won't be a way to make the bases the same. And so then we'll go to logarithms to help us solve that. Questions or clarifications on this? Okay, there is a little note there that simply states what I just said. If you can't get the bases the same, you're going to use your logarithms to solve. Now, that's if we're solving exponential equations. If we're going to solve logarithmic equations, then we have a different set of steps that we have to go through. If you're using your logs to solve exponentials, oh, that's what it was. Sorry, I read it backwards. I read exponentials. We will solve logarithms as well today. But if you're doing the logs to solve the exponentials, that's what we actually just did in the last one, the first way we did it. You isolate your exponential expression. If the base is 10, you'll take the common log of both sides. That never happens. It really doesn't. Because almost always you have a base of 2 or a base of 12 or something like that. If the base is not 10, you'll take the natural log of both sides. And then you'll start simplifying using various rules that we've encountered. You'll use your exponential rule like we just did, where we pull the exponent out front of our ln. Or you'll remember one of these two special rules where if we're taking the log with the same base as our exponential, then those go away and we're just left with whatever that exponent was. Same thing over here. We're taking log and it's base 10 of 10, which means we just are left with our exponent, and that helps us to simplify things. And then we just solve for the variable. In here, I think they had you round to 3 decimals in this section. I kind of hate that Pearson isn't consistent. Some sections it's 4 decimals, some sections it's 3. Just make sure that you're paying attention to whatever Pearson is asking for. You will be dealing a lot more with decimals in today's lesson. Okay, so these problems are going to be ones that there is no way we can make the bases the same, and so we're going to have to work with using our logs. And I will try my best to keep the instructions on the screen at the same time, at least for the first one. We're going to do 3 to the x equals 20. I can't take 3 to any power and get us over to 20. At least not a nice whole number, not a rational number. And so what I'm going to do is I'm going to ln both sides. Again, because my base is not 10. My base is 3. So I'm going to choose to ln both sides. And then I will use my power rule to pull that exponent out front. That's an n. Whole goal here is to isolate my variables, so I'm going to divide both sides by ln of 3. And then I go to my calculator. ln of 20 divided by ln of 3 is approximately, can you see my approximate? Not quite. Approximately 2.7268. I went to 4 decimal places in my handwritten notes, but like I said, Pearson, for some reason in this one, only went to 3. So this would be 2.727 in Pearson. Is there one in this one that's annoying? Or is that my other class? I think it's my other class. Oh, no. There is one in your homework I'll go ahead and warn you about. Number 14, it was annoying to me because you get a fractional answer, at least the one that I did. You get a fractional answer, and I'm used to leaving fractions as fractions, and of course I didn't read the little blue words. And the little blue words next to the box says, type an integer or a decimal. Well, integers are a whole number, and then there's decimals. So the fact that I had a fraction, it took me 2 tries, and I was like, oh, well, I need to do that. But then like 3 problems later, you're using a fraction. That's what I don't like. So just be aware, 14, they want a decimal. Questions on this one? How it worked or any of that? All right. Let's look at B. (100e raised to the 0.08t equals 2500). Step 1 of our process is to isolate our exponential expression. Right now it's not isolated because it's got that 100 attached to it. So I'm going to divide both sides by 100 so that I'm left with e to the 0.08t equals 25. Now my exponential expression is totally by itself, and I can't set 25 as e to something, so I'm going to ln both sides. So I have ln of e 0.08t equals ln of 25. Now the natural log, that ln, is log base e. So when you're taking log base e of e, it goes away. So what I really have is I have 0.08t equals ln of 25. So to find out what t is, I would divide both sides by the 0.08. And even though my notes are rounded, oh, this one's only rounded to 1 spot. Let's see if that's because that's all there is. ln of 25 divided by 0.08. No, there's more than that, so I don't know why I stopped rounding. 40.236. Questions, clarifications? All right, let's do one that's slightly more complex. This one's more complex because we're going to have 2 exponentials that play. So even if you're playing around with more than one exponential at a time, you're still going to follow the exact same steps. You want to start by isolating one of the exponential expressions. And luckily for us, this one's not more complicated by having any additional terms besides the exponentials. So both of our exponentials are actually completely isolated. So we're good. So what we're going to do is we're still going to ln both sides. My base is not 10 on both of these, so I can't use that. And like I said, you will almost never use it just because it's so limiting. So I'm still going to ln both of these. And then I use my power rule to pull my power out front. Now one thing I will say is when you have a power that has multiple terms, or is a binomial like this one, when you pull it out front, make sure that you leave it in parentheses. Because if not, sidebar, if I just write x plus 3 ln of 4, that's totally different. This would be x plus ln of 4 to the 3rd. These are not the same thing. And so you want to be careful and use those parentheses so that you actually mean what you mean. All right, let's ignore the sidebar. Then over here, I pull out my negative x to the front. Now, the whole goal is to get my x by itself. And right now I have x on the left, I have x on the right, so that's not happening. And I have this x inside this parenthesis here. So I'm going to have to distribute the ln4 to each of those so that I have x ln4 plus 3 ln4. And I'm going to go ahead and subtract or add over this negative x ln3. And just get everything over on the left, at least for a moment. Because I got to get all my x terms together. I can't combine them because I have ln of 4 and ln of 3, but I can still group them together. So in order to make sure that I only have terms with x on the left-hand side, I'm going to subtract this 3 ln of 4 over to the other side. Now, what do I do next? Remembering I'm trying to solve for x. I got to factor out that x. Exactly right. I got to pull that x out so that I have ln of 4 plus ln of 3 equals negative 3 ln of 4. Because once I've factored out that x, notice there's only one x term left. And that x is multiplying against everything in the parentheses. So if I'm trying to isolate that x, I'm going to divide everything that's in that parentheses over. Negative 3 ln of 4 all over ln of 4 plus ln of 3. And even though this takes up paper space, you want to make sure that when you're working these logarithmic problems that you do it on paper as long as you possibly can. If you start typing in stuff into your calculator up here, it's going to round. And then when you come down here, you're going to be rounding some more, and you're going to get further and further away from the actual answer. And your problems in Pearson actually tell you that. They tell you do not round until the last step. This is the last step. This is what you'd need to type into your calculator to figure out what x equals. Until this point, you don't want to do any rounding. You want to leave it in logarithmic form. So once you type that in, we find that x is approximately 1.674. Negative. I mean, hold me accountable. I'm going off my notes. I'm not actually using the calculator for most of this. So if I'm not right, tell me. Negative 3 ln of 4 divided by ln of 4 plus ln of 3. Negative 6. Yeah, that's what I got. Right? Okay. Don't make me question. It's Friday. It's late. Who knows?
It's just the rounding point. Sometimes it's 2, sometimes it's 3, sometimes it's 4.
So in my handwritten notes, like I said, it should be 4 on all of them. I don't know what happened with B there. But I noticed in Pearson, in this particular homework assignment, they rounded everything to 3 decimal places. So I'm trying to adjust live, which is always a little bit risky. So if you can't make the bases the same, or you don't recognize that the bases of your exponentials could be the same, you're going to ln or log both of them, depending on what your base is. Almost always it's an ln. And then you're going to isolate the variable and solve. And again, wait until the very last possible second to type anything into your calculator so that you're not rounding multiple times throughout the problem. Questions or clarifications or anything I can clear up before we move on? Because those are the 2 ways we solve exponentials. All right, then let's look at how we handle logarithms. If we solve exponentials using logarithms, we can make a logical deduction that we are going to solve logarithms using exponentials. Let me zoom out a tiny bit. We are literally going to use our definition of a logarithm in order to solve logarithmic equations. So the first thing you want to do is you want to isolate your logarithm. Get it by itself. So you have log base b of m equals c, or you could have ln of m equals c. It works for the natural log just as well as a regular log. Then you're going to convert from your log to the exponential. That's the whole, the base becomes the base, the answer becomes the exponent, what you were taking the log of becomes your answer, that jazz. You want to solve for your variable, and you want to check your solutions. We can only keep values where m is positive. Remember, we can't take the log of 0. We can't take the log of negative numbers. So if our solution causes us to have a negative, a negative within your logarithm, then we have a problem, and we can't include it. It's called an extraneous solution. Now, that doesn't guarantee that what we found for our variable can't be negative, because it really depends on what expression is within our logarithm itself. Sometimes positive numbers are going to break our logarithm. Sometimes it's negative numbers. The big thing is whatever this expression is has to be positive in the long run. That's the goal. And so you kind of have to do a little bit of a check at the end to make sure that all your solutions will work. When it comes to the logarithms, we're going to use every rule that we've learned. We're going to use our product rule, our quotient rule, our power rule. We're going to use them all. Because notice this says we have a single logarithm equal to a constant. It doesn't say we have a string of logarithms, so we're going to have to use our condensing methods in order to condense down into a single logarithm before we can actually convert over to our exponentials. So we're going to have log of x plus log of x plus 3 equals 1. Right now we have 2 logs on the left. We can't do that. But we learned a lot of different rules that we can combine our logarithms. So what rule am I going to utilize here? The product rule. Yeah. I can combine these using multiplication. This will be log, and then I'm hoping we can keep up with this. We're going to be multiplying x with x plus 3. So I was going to skip that middle step and just put the x squared plus 3x. I distributed that x into each term. I hope at this point in the semester we can do that. And if not, you can always write it out. But now we do have a single logarithm, and we have a constant on the other side. So now I'm going to use my base becomes the base, the answer becomes the exponent. But there's no base listed right here on this log, so what is the base? 10. This is our common log. So when there's no number written here and it just says log, then that means it has a base of 10. So the base of my logarithm becomes the base of my exponent. Base becomes the base. The answer of my logarithm becomes the exponent. And then everything else that I was taking the log of becomes my new answer. Well, 10 to the first power is 10. I'm going to subtract that over to the other side because it looks like we have a quadratic to play with. So now I'm going to factor. First term is x squared, so that gives me an x and an x. The sign in front of my c term is a negative, meaning I'm going to have a plus and a minus. So I need factors of 10 that subtract to give me 3. Well, the factors of 10 are 1 and 10, or 2 and 5. 2 and 5 would subtract to give me 3. 3 is positive, so I need to have more positives than negatives. So I'm going to have a plus 5 and a minus 2. Using my zero product principle now, I can set each of these factors equal to 0, and I can figure out what x equals. Now this is where you would like to be done, but you're not quite. You're almost done with it. we have to test these to see if they work. And before you're like, oh, I don't want to have to plug the whole thing in, you actually don't. This problem is exceptionally nice because if you go all the way back up to the beginning, look, we have log of just single x. Well, if x is -5, that's log of a negative number. That doesn't work. So you don't actually have to plug in, do any real typing in of anything. It's just a little bit of logic and looking at what happens. So this one doesn't work. That would be an extraneous solution. And then if you wanted to test in your calculator whether or not this would work, you totally can. More times than not, it's not really testing to see which ones are accurate. It's trying to find those trouble spots, those extraneous solutions. That's really more what the testing of the solutions is. But you can totally plug into and type it into your calculator and figure out if it works. It does. But something I want to show you is if this problem was just the log of x plus 3, -5 would still break it, and -3 would still break it. But -2 as a solution would not break this logarithm. That's why x is being negative doesn't guarantee that that's going to screw up our actual problem. It depends on what the expression is in here. So don't just assume, okay, we're always going to mark out the negatives, because that's not always guaranteed. And sometimes our positives are going to break this. We just have to pay attention to what's inside of our logarithms. All right, questions on how this problem works? All right, let's do another one. Let's flip this over. I'll rewrite it in marker so it stands out. We're going to do log base 3 of 2x minus 1 minus log base 3 of x minus 4 equals 2. So again, we have multiple logs, but we know lots of good logarithmic rules. Since there's a minus between these two logs, and since they have the same base, we can combine them using our quotient rule. Our quotient rule will have log base 3, and then whichever term was first, whichever log was first, that's the one that becomes our numerator, our top. So it'll be 2x minus 1 all over x minus 4, and that equals 2. So we condense down the left-hand side into a single logarithm, and now I can apply, my base becomes the base, the answer becomes the exponent. The base of my logarithm is 3. So base becomes the base. My answer was 2, so that becomes my new exponent. And we set that equal to the 2x minus 1 all over x minus 4. Well, 3 squared is 9. And notice I have an x both in my numerator and my denominator, so I'm going to have to multiply my denominator over so that I can start moving things around and isolating my variable. So if I multiply by x minus 4, I'll end up with 9x minus 36 equals 2x minus 4. Now I'm just working on isolating my variable. I'm going to move my x's to the left and my numbers to the right so I can keep a positive exponent, or excuse me, positive variable. Subtract the 2, that'll give me 7x. Add the 36, that'll give me 35. Divide both sides by 7, and I get that x is 5. Now, when I go back up to test in the original problem, what I'm checking for is making sure that's what's inside my parentheses will stay positive. 2 times 5 is 10. 10 take away 1 is 9. This is positive, so that's okay. Over here, what I'm doing is I plug in a 5. 5 minus 4, that gives me 1. I can take the logarithm of 1. That's okay. So x is 5 works. Questions, comments, clarifications, things you see I'm doing wrong? Hopefully not.
So why did we use the x minus 4?
Well, because we're trying to isolate the x's, but we have an x on top and on bottom.
Okay.
So if I multiply both sides by x minus 4, that moves it over. Because right now it's dividing on this side. So if I multiply it over, then that gives it to where I can start moving my x's around.
I mean, it makes sense after we've gone into this. I just want to know how I would be able to do that.
Yeah. I mean, if you wanted to, another way of thinking about it is you have 9 over here. If you put it over 1, you have a fraction equal a fraction, and you can cross multiply. So if that way clicks with you, you can also do that. Other questions or clarifications? Okay, I'm going to give you a little additional rule. It ties back to our first rule with solving exponentials. Here we said if our bases are the same, we can completely ignore those bases and just set our exponents equal to each other. There's a similar rule for logarithms. And it's if log base b of m equals log base b of n. Whoa, sorry, that was like way crazy. Then m equals n. So if I can set up my equation in such a way that I have a single logarithm on both sides and they have the same base, then I can completely ignore those logarithms and I can just look at whatever the logarithms are being taken of. And that's really nice. None of our problems have been eligible for this, so don't think that we've been like getting cheated out of something. We haven't. Because even on this last problem where we did have multiple logs, we also still had this constant, and that would have messed it up. Because that's not log base 3 of anything. So we still couldn't have used this rule. But we're going to get to use this rule in the next one. So for C, okay, good, that's on there. We have ln of 4x plus 6 minus ln of x plus 5 equals ln of x. All kinds of ln's. Right now, I can't apply that rule that I just told you because I have 2 different ln's on the left and 1 on the right. I need to have 1 ln on the left and 1 ln on the right, and then I can apply that principle. So I'm going to use my quotient rule again to combine the 2 that are on the left. So I have ln of 4x plus 6 over x plus 5 equals ln of 5. I don't know why I wrote 5. I just did. Of x. Now that I have a single ln on the left and a single ln on the right, I can apply that rule to where I can completely just ignore the ln's, and I'm left with 4x plus 6 over 5 plus x, since I keep wanting to say 5 first, equals x. And then this is similar to the last problem where we had it set equal to 9. In order for me not to have an x in my denominator, I'm going to multiply both sides by the x plus 5. Or you can think about it by putting x over 1 and doing cross multiplication, whichever way works best for you. I'll be left with 4x plus 6 equals x squared plus 5x, either way. Since my x squared is positive on my right-hand side, at least the way I have it written, I'm going to move everything over so that it's another quadratic problem by subtracting the 4x and subtracting the 6. Then I got a factor. Sign in front of my c is negative, so I'm going to have a plus minus inside. Factors of 6 that subtract to give me a 1 would be 3 and 2. Since it's a positive x here, I'm going to have a plus 3 and a minus 2. Zero product principle, I set each of them equal to 0. And I find that x is negative 3 or x is positive 2. Once again, we actually luck out because in our original problem, we have ln of just a single x. So that's the easiest one to check. So if I plug in x equals -3, that breaks this one, so I can't include -3 as part of my solution. Now, I would still want to check to make sure that the 2 doesn't break either of my others as well, but checking for when x is negative, if you have just ln of a single variable, that's the easiest one to check. Because if you look at, that one would have broken over here too. But like ln of x plus 5, if this is -3, it wouldn't have broken this one. So you always want to make sure and check and be comprehensive or conclusive on all of it. So the only answer is 2. Questions, comments, clarifications? How are we doing? Okay, I got a thumbs up and a head nod, so that's pretty good. Flipping it over. All right, let's do another one. You can't. Yes, you can. We're going to do log base 6 of x equals 1 minus log base 6 of x minus 5. So when we're solving logarithms, the first thing we have to do is we have to get our logarithm isolated. I can't use that special rule where I have the same log with the same base on both sides and just ignore them, because that 1 is not log base 6. So I can't do that. So I'm going to need to add this log base 6 of x minus 5 over to the other side so that hopefully I can condense my logarithms into a single log. So I'm going to add all of this, my right-hand log, to my left. So I have log base 6 of x plus log base 6 of x minus 5, and all of that equals 1. Now using my product rule, I can combine this to where I have log base 6 of x squared minus 5x equals 1. Using the definition of a log, base of my log becomes the base of my exponential. Base becomes base. The answer of my log becomes the exponent. And what I was taking the log of becomes my new answer. I'm going to subtract that 6 over so that I have a quadratic. Then it's time to factor. Again, the sign is negative here in front of my 6, so I'm going to have a plus minus. I need factors of 6 that subtract to give me a negative 5. Well, 1 and 6 would subtract to give me a negative 5 as long as my 6 was the negative. Be careful on that one because you might be tempted to put 2 and 3 because 2 and 3 add up to 5. But because this is a minus here in front of my 6, they are subtracting together to give me that 5. Set each of my factors equal to 0 and find that x is negative 1 or x is positive 6. Gosh, I gave you all nice ones for this one because this one's got log base 6 of x, so the fact that x is negative 1 breaks my logarithm. X is 6 would work here, and if I plugged it in here, I would end up with log base 6 of 1, which works over here. So the only solution that I have is x equals 6. Are there any questions on any of those?